do momentum and impulse. So we're going to talk about momentum in the context of what is called a collision. Now, I'm sure everybody knows what a collision is, but we do need a scientific definition because this is the definition that we're going to adhere to. So collisions, you often think about vehicles or maybe football players running into each other and etc. However, in this class, the scientific definition we're going to be using is any short duration interaction, short duration contact interaction, I forgot that word, contact interaction, between two objects. Short duration contact interaction between two objects. So indeed, two cars colliding, that is indeed considered a collision. However, stuff that you normally would not associate with collision would also fit into our scientific definition. One of the scenarios that we're going to go over is a person, Sam knows because you came early and heard one of our arguments. A person is going to jump onto a cart. That is also considered a collision because when you're going onto the cart, it is a short duration contact interaction, okay? So you can't limit yourself to just what you think is a collision. It's really, does it adhere to this definition? That is a question. Now let me, yeah.
I just have a quick clarifying question. Would any quick push, like the force push, count as a collision, like a baseball bat hitting a baseball?
Correct.
Does that count? Okay.
Correct. Yes. So let me now go over what a collision even is. So that's the definition, but let's go over the entire scenario. Man, I can't draw a straight line. So let's say this is the wall, and we hurled a ball onto the wall. So originally, let's say it's going at this speed v. Let's say this is scenario 1. Now, whenever there's contact, or whenever there's an interaction, there is going to be a force that is exchanged between the two different objects. So what we care about is looking at the force of the ball, of the wall onto the ball at the various time points. So let's call this scenario T1. Well, at this scenario, is the ball interacting with the wall at all? And the answer is no. So in this scenario, the force is actually going to be equal to 0. Now, let's say at a later point, let's say snapshot 2, the ball is just making contact with the wall, just barely touching it. Because it's just barely touching it, the force is still going to be approximately equal to 0. Let's say that is T2. But as we take consecutive snapshots, you're going to notice that the ball actually begins to deform a little bit. It actually truncates. And so here, the force of the wall onto the ball this time is going to be greater than 0. So at T3, we now have some finite value of the force in between the two objects. Now at a later point in time, let's say time 4, it's going to have its max, it's going to be absolutely pancaked. This is going to be the max deformation. So at this point, it's going to have reached the maximum force value. So let's say this is T4. And then the later points, so 5, 6, and 7, it's just going to be the reverse of that. So in scenario 5, it's going to begin to decompress slightly. And at 6, it's going to retain its original shape. And in scenario 7, the ball is now coming off with some speed v. Then the force profile would also be symmetric. Like the following. Yeah, so if we had infinite number of data points, the force profile would look something like this. And this is what would be occurring in a collision. It doesn't matter if you have a bouncy ball or a steel ball, they all do this to some extent. So even if it's steel, stone, boulders, whatever you want to call it, they all do this kind of deformation. And during this point, we would say the object is compressing. So compression. Here, it's doing expansion. So one thing to notice is that the amount of force in between the two objects is a function of time. At a different time point, the value of the force is different. The value of the force changes. Now, because these are happening on such a short time scale, it's actually really, really hard to get these discrete data points, and it's really, really hard to get this overall profile. What we actually observe is what happens right before and what happens right after. Those are fairly easy to obtain. And so we actually don't care about what is the force at this value or what is the force at this value or so on and so forth. What we actually care about is what is the total force that's been transferred. What is the total force that's been transferred? So instead of looking at the value at each point, what we actually care about is this entire area. This area is the total force that's been transferred between the wall and the ball. Now that's the graphical interpretation. However, we need a numerical one. And the answer to this is Newton's second law. Now the force, we see that is a function of time, but Newton's second law says that this is actually equal to mass times acceleration. Right? Newton's second law, F is equal to ma. However, one of the things that we discussed was that acceleration is actually change in velocity over change in time. Meaning, mass times acceleration is actually equal to mass times delta v over delta t. As a reminder, delta v is equal to v final minus v initial. Meaning m delta v is equal to m vf minus v naught. But one of the things that we can do is distribute the mass to both of these terms. So we can say this is mvf minus mv naught. So essentially, we de-simplified it. We made it a little bit more complex. But the reason why we did that is this is now equal to delta of mass times velocity. So m delta v is actually equal to delta mv. Meaning, we're going to substitute this m delta v over delta t. We're going to substitute that to be delta mv over delta t. And if you thought this was Newton's second law, it's not. This is actually not Newton's second law. This is actual Newton's second law. F equals ma is just a simplified version of what Newton actually wrote. Except I kind of lied again. Instead of actually writing mv, he defined m times v as what is called momentum. M times v is what is called momentum, and we give it the notation p. We give it the notation p. So what Newton actually wrote was delta p, delta t. This is Newton's second law. So momentum is what Newton actually thought was pretty much the most important concept, and that's mass times velocity. Mass times velocity. Now with this expression, we can get what F total is actually going to be. Delta P is going to be F, we'll call it F average times delta T. So in our force versus time graph, we had this kind of a shape. However, instead of, now finding the area of this is actually very, very complicated. Instead, an object that we can find an area for very easily is a rectangle. And this value is F average, and this distance we call delta t. As long as we define F average correctly, the area, although I didn't draw it correctly in here, so let me kind of redraw this. All right, let me redraw it. As long as we define the average force properly, we can draw a rectangle where the areas are the same. What is the area expression for a rectangle? How do you get it? Base times height. Base is delta t, and what is our height? F average. That is what this is. F average times delta t is that area. Meaning delta p is equal to F total. So if you want to know the total force that was exerted onto the ball, all we need, delta P is mass times final velocity minus mass times initial velocity. This is equal to F total. In our collision example, mass of the object is typically given. The only other information you need to get the total force is the final velocity and the initial velocity. That is it. And those you can very simply get just by taking a video and then getting a snapshot. And so you just multiply this by mass, that by mass, take the difference, and that is the total force between the two objects. Yeah.
So I'm just a little bit confused. How come the base of the rectangle is delta t if the movement of the ball extends from x or from t equals 0 or from like the t 0 of the t-axis
Yeah,
to
so
further?
when we're doing what is called the well, actually I don't know what it's called. We're making an approximation, and that approximation is we just need the two different areas to be the same. That's it. And we can define this F average as half the peak and then change that delta t. Does that make sense? So we're just making an approximation because getting the actual area is extremely, extremely difficult, because that means you would need an infinite series of snapshots, and some objects deform or barely deform, such as metals, that it's almost impossible to get a force profile like this. And so instead we just approximate it as, all right, we know when it makes contact, we know when it doesn't, so that's an approximate value of delta t, and we can get the different velocities coming off of it. And as long as you know the mass, then you can get the total force that was exerted between the two. Yeah.
Is F average and F total the same thing?
No. F total is F average times delta t.
Oh. So is the is the area of the rectangle F average or F total?
F total.
Oh.
F total. Oh, so this is okay, F average per time. So, there's another way to get the net force acting on an object, and you do not need to do the force balance of considering all the different forces acting on the system. Another way is to just simply get the final and the initial velocity and multiply it by the mass. So let's actually apply, so the change in momentum is actually very, very important and very, very useful for a lot of different scenarios. So let's make sure we know how to compute the change in momentum correctly. So let's do a simple example. We want to know what is the cart's change in momentum. So the initial scenario, we have a 10 kilogram cart. It moves this way at 2 meters per second. After the cart hits the wall, bounces back, and it's now only traveling 1 meter per second. Is it A, negative 30 kilogram meters per second. Or is it B 0, C 10, D 20, or E 30? And they all have the same units. Who thinks it's A? Raise your hand. Negative 30 kilogram meter per second. Who says it's B? All right, who's still writing the problem down? Seems like most people are. All right, who has a guess for the solution? Anybody? Say it.
30.
This one, 30?
Yeah.
Or negative 30?
Positive.
Positive 30?
Yeah.
Any seconds? Wow, no support, Sam.
That's fine, bro.
Oh, we got one.
Yeah.
All right, well, let's see if that's true. Delta P is P final minus P initial, which is mass times velocity final minus mass times the initial velocity. In our scenario, we're only going in the x direction. So in the x, we could say delta P is equal to mass times the final velocity of our scenario. Which direction is the cart going? Positive x. It is the velocity, the direction does matter. So positive 1 meter per second. Minus mass times initially, which direction is the cart headed? Negative x direction, so it's minus 2 meters per second. We see a double negative, so those become plus. And so then this is actually equal to 3 times n, meaning it is indeed 30 kilogram meters per second. Because the mass is 10 kilograms, yeah.
Wait, why is 2 meters per second positive? Shouldn't it be negative?
Yeah, but there was a minus and negative. Because it's a minus and negative, it turns into a positive. And so this 30 was indeed correct. Now let's do a thought experiment. I'm going to ask you guys a question. Which would you rather be hit by? Is it A, 10 kilogram rubber ball, which bounces with same V, or B, a 10 kilogram steel ball, not with bounces, but which bounces, which hits and stops. All right, let's assume you all like to avoid pain. From then, which one would you rather be hit by? A rubber ball or a steel ball? They have equal weights and they're going to be coming at you at the same speed. Which one?
Maybe steel.
You want to be, you're trying to minimize pain? Do I really ask the trick question? Wait, really? You'd rather be hit by a steel ball?
I don't know, because doesn't the rubber ball like kick off you then if it bounces? Would that impact at all, or?
Yeah, but you're already thinking about physics. I'm just asking you to think about. I have a steel ball and a rubber one. You have to be hit. Which one are you going to choose?
Probably the rubber one.
Right, probably the rubber one, right? All right. So let's do the analysis. The reason why I'm asking this question is many people do this analysis wrong, but you get to the same answer. And the worst scenario or the worst position you ever want to be in is getting the correct answer but for the wrong reason. Because that means you think you have mastered something but you're totally deceived, and that's when tragedies happen. So, let me give you the wrong way before I give you the right way. Likely, you want to be hit by the rubber ball, right? Rubber will likely be less painful. So we know that delta P is equal to the total force that was transferred. This is going to be P final minus P initial. Which, if it bounces with the same V, you're going to have mass times V minus mass times V, because they're going at the same speed. This is going to equal 0, meaning this is the total force that the ball exerts on you is going to be what? 0. Therefore, it's going to be much less painful than the steel ball. Except this is wrong! Like I said, this is the wrong analysis that will lead you to the correct conclusion. Well, let's try it comparing it to the steel. And we're still going to do the wrong approach, okay? Delta P is, we know there's going to be F total. This time, P final, because it stops, it's not bouncing off of you, what is the final velocity? Right, it's going to be 0, meaning it's mass times 0 minus mass times it's coming at V, meaning it's negative mv. So this is if you chose the rubber, and this is if you chose the steel. And notice, the steel one actually has a magnitude of a force. So therefore it's going to hurt. That's what the improper analysis would give you. But like I'm saying, this is the wrong conclusion. But you could see how convincing, or this is how you get to the correct conclusion, but for the wrong reason. Notice you're going to see, look, 0 force, oh yeah, that makes sense. We did the momentum calculation correctly, but we did not. And another thing I want you to see is when we actually do this correctly, you're gonna get a very confusing answer. So let's actually do the solution, or problem correct. For the rubber, delta P is equal to F total. PF minus P naught. The reason why this expression was incorrect is, let's say this is U. Ball's coming this way. What is the initial velocity? Or sorry, what is the final velocity? If the rubber ball bounces, it's going to come off this way, and it's going to go in the negative x direction. So it's mass times negative v. What was forgotten here was that we did not use momentum as a vector quantity. Momentum is a vector, therefore we do need the directionality of the velocity, not just the speed. It's going in the negative x direction, so that negative was indeed necessary. And then it's minus the initial velocity, which is mass times what direction is the ball originally traveling? Positive x direction, so it's positive v, meaning you get negative 2 mv. This is defined as your total force. Whereas the steel, delta P is equal to F total. For the steel, this analysis is actually correct. It indeed does stop. So the final velocity is 0, minus the initial, which is actually going in the positive x direction. And so you're going to get negative mv as your total for steel versus total for rubber. This is the correct answer. But what do you see surprising? Yeah.
Rubber's double the force.
Yeah, the rubber has double the amount of force. So how can this be correct? So when we do the correct analysis, we seem to get the wrong conclusion, something that seems aphysical. However, I'm here to convince you this is actually true. The reason why... Alright, so now who wants to get hit by the steel ball? Raise your hand. No, the answer's still wrong, and this is the reason why. The amount of force that you transfer between the ball is actually much greater for the rubber. However, and that graph may look something that looks like this. But with the steel, it's going to be, so remember the total force is this area. With the steel, you're going to have a much smaller area, that's true. However, it's going to happen in a much shorter duration, and it'll look something like this. And what you feel as pain is not the total force that was exerted, but we'll call this force as your ouch force, where you would actually say ouch. What you feel as pain is the instantaneous force. At a specific moment, how much force is actually interacting between you. And you can see, for the steel, you actually have a higher peak force than the rubber. And that's why you still want to get hit by the rubber. So let me ask you guys a question. Would you rather be hit by, I don't know, like a sandbag that's covered in like 50 layers of foam? Or something, I don't know. I can't think of something. But ultimately, if you just encase whatever, let's say it's like a hammer, but you encase it in a lot of foam, it's not going to hurt anymore. Because that foam is, instead of making it a very sharp peak where all of that interaction is happening over a short period of time, that foam allows the interaction to happen over a much longer period, which brings this peak force down. Does that make sense? That's why it hurts less, yeah.
Does the height of the peak force have to do anything with how moldable the object is when sliding into the object?
Yes. Because you know exactly what your change of momentum is.
Right.
Like for the steel, if it hits and stops, you know what this overall area has to be.
Right, because
And if you just time it, you'll know when it's actually doing the compression versus it decompresses and stops. So you'll know that duration.
And that happens faster than it would if it was a rubber ball because it doesn't have the ability to like shrink
So
as much.
steel would happen faster than rubber.
Yes.
Yes, yes. Okay. Yeah. Because, yeah, steel doesn't want to deform.
Okay, so it would reach its max ability to deform faster, which would be.
Correct, yes. So let's say at this point, that's when the contact was made. Technically, it should look something like this. The steel would completely finish, whereas the rubber still continued to compress. And in actuality, the rubber happens, I think, close to 1,000,000 times longer than steel. So close to 1,000,000 times longer than steel. So that's what it would look like. So we'll write some of that into words, even though rubber has larger delta P, hurts less because collision occurs over a longer duration. Alright, and so that's a little primer onto momentum. Now we're going to go about conserving momentum. Let's do conservation of momentum. Simply stated, we can do this from Newton's second law. We discussed that the net force is change in momentum, so delta P over delta T. Delta P over delta T. Now, if a system is isolated, and by isolated, what we mean is the net force is equal to 0. If F net is equal to 0, then 0 is going to equal delta P over delta T. And of course, we can multiply delta T by both sides, meaning delta P is going to equal 0. And if delta P is equal to 0, what we can say is that the final momentum is equal to the initial momentum. This is conservation of momentum. So if the delta P is equal to 0, that means the initial and the final are the same, and if it's not changing with time, it is constant. Momentum is conserved. in general, so let's use the generalized form. If isolated, then we're going to use the capital P. This is the total momentum. PF is equal to P naught. Where P, capital P, is equal to the sum of the different momentums that constitute the system. So if there's multiple objects, then you have to add up the different contributions. Meaning, P1F plus P2F plus so on and so forth is equal to P1 naught plus P2 naught plus so on and so forth. So this is the generalized conservation of momentum. The total doesn't change, meaning the final is equal to the initial. And so let's do an example putting this into use. And this comes straight from Newton's second law. Okay. So let's say Bob runs at 4 meters per second onto a 25 kilogram cart that is stationary. Let's say Bob is the typical body mass of 75 kilograms. And we want to know what is the final speed, or what is Bob's final speed. So in our sketch, we have our little cart. It goes onto our cart. Then after he jumps onto the cart, his momentum is going to carry himself and the cart forward. Now the things that we know are mass of Bob, mass of cart. We know the initial velocity of Bob is 4 meters per second. The initial velocity of the cart is 0 meters per second. And once Bob jumps into the cart, we also know one additional piece of information. What is that one additional piece of information? If Bob jumps into the cart, what is true?
They share the same acceleration.
Yes, share the same acceleration and velocity. In our case, for momentum, velocity is a more important parameter. The final velocity of Bob is the final velocity of the cart. Because we know that's true, let's just call it a generic VF. Now, what are we looking for? we are simply looking for what is VF. That is what we care about. Now, in these types of problems, when you read it, or at least when you get to the final, we're going to have covered kinematics, we're going to have covered dynamics, 1D, 2D, you know, all, as well as conservation of momentum, conservation of energy, so on and so forth. So you're going to have covered quite a few different types of problems. So let me just give you some guidance on the thought process to eliminate, or at least narrow down, what the proper approach would be. So note that we have a before and after scenario. If you have a before and after scenario, we saw this in kinematics. Remember, the initial angle was yada yada yada, the initial speed was blank, how far did it go, so on and so forth. So if you see a before and after, it's either kinematics or one of those conservation laws, or conservation of energy or momentum. So in these types of scenarios, it's likely not going to be a dynamics problem. But also note, in this scenario, Bob and Cart are interacting. Where Bob and the cart, we care about both of these as objects. In kinematics, you're really only going to be focusing on a single object, which is going to be the ball or something like that. In the midterm, there was that baseball problem. Right, in the baseball problem, we cared about how far the ball goes, but we didn't really care about the motion of the bat whatsoever. In this scenario, we care about Bob and the cart, and they're interacting. And if they're interacting, this should immediately lead you to think, oh, third law, for every action there's an equal and opposite reaction. Or in this case, it is the conservation of energy / momentum. So if you have both of these conditions met, that it's a before and after scenario, as well as there's some meaningful interaction going on, likely it's going to be a conservation of momentum problem. So we can actually start here. P final is equal to P initial. Now in this problem, one of the things that you have to do precisely is identify your system appropriately. The net force of your system has to be equal to 0. That is one of the conditions that went into our derivation. It's only if we have an isolated system do we actually get the conservation of momentum relationship. Here, our system cannot be just the cart, because Bob is now exerting a net force onto the cart. Does that make sense? Also, it can't just be Bob, because when Bob jumps onto the cart's going to have a reverse force onto Bob. Instead, what the system needs to be is both Bob and the cart combined together. And in the final scenario, this is going to be our system. If we define Bob and the cart as our system, whatever Bob does to the cart or the cart does to the Bob, it's within our system, so there's no outside net force, and so our condition holds. So then our final momentum is going to be mass of Bob times the final velocity of Bob plus mass of cart times the final velocity of cart. This is going to be equal to the mass of Bob times the initial velocity of Bob plus mass of cart times the initial velocity of cart. But we noted up here that once Bob enters a cart, they are moving in unison. The velocities are going to be the same, meaning we have on the left-hand side mass of Bob times mass of cart times VF is going to be mass of Bob, V naught Bob. What is the initial speed of the cart?
0.
It is 0, so we can just get rid of that. And we're only considering the x direction, so the x component. And so we have VF is equal to mass of Bob over mass of Bob plus mass of the cart times the initial speed of Bob, which is going to be 75 kilograms over 75 kilograms plus 25 kilograms times 4 meters per second, and you're going to get 3 meters per second as your solution.
What does the subscript say next to the M and then the initial
This one?
velocity? Yeah.
It's mass of Bob.
Okay.
Dutch
Yeah.
What is it that in this system final momentum is equal to the initial momentum? Why is it that it's conserved?
Because the net force of our system is equal to 0. What is the net force acting on our system? Well, in our system, Bob is going to be essentially pushing the cart that way, right?
That's right.
The cart is going to be pushing Bob backwards because of Newton's third law, right?
That's right, yeah.
So if you add the two, and these are happening to each other, and they're both inside the system.
Right.
So what we actually care about is, let's say we have this, mystery box as our system. There can be stuff going inside all at once. But all of this is contained inside, so there is no net force acting on our system.
Oh, right.
So it's only if, let's say, there was a great gust of wind coming this way, then momentum is not conserved because now we have a net force. However, I'm sure whoever had siblings, you guys all blew in each other's ear or tried to annoy each other, whatever. Who's done that before? Raise your hand. Yeah, you can do that. You can have a wind blowing fight all you want inside your system, but then the net force is still going to be 0 as long as they're inside the system. But if there's a great gust of wind coming from the outside, then it's not equal to 0 because you now have something acting on the system
Right.
from the outside.
That makes sense. Thank you.
Well, I was just joking, but you guys really do it? That's it. No, I'm just kidding. I get that all the time. Now, in these problems, the problems really don't get much harder than this. You do use final is equal to initial, and then it is just simply a rearranging problem. So, I'll say the most difficult portion of the class is kind of behind us. And the reason why it's kind of is for like one lecture, it's going to pick up again because we're then getting into rotation. And then we're gonna revisit all the difficult things that we just visited again, but in a condensed format. But for now, it's actually very, very simple because everything is just final is equal to initial. As long as you are considering the system properly, the number is just going to fall right out. Now, even though conservation of momentum problems are simple, But the trade-off is that it is limited. And to convince you of this, let me give you an example. So consider a bouncy ball. Let's say you just dropped it at rest, meaning your initial velocity is equal to 0. At a later point in time, before it hits the ground, let's say it's going to be down here now, which direction is the ball headed? Where's it going? All right, it's going to have a speed down. So between 1 and 2, ball is in free fall. Therefore, we see that V1 is greater than V0. We know this is true. But let's try applying conservation of momentum. But conservation of momentum, we're going to do P final is equal to P initial. And we're only considering the y component. Well, what's our final? It's mass times V1. Well, what is our initial? Mass times V0. You can see that the masses cancel. And if you apply conservation of momentum, what relationship do you find? This will tell you that V1 has to equal V0. However, this is clearly not true. We have something occurring where V1 is greater than V0. We know this is true, but conservation of momentum seems to be failing us. But this is wrong. And what is the issue?
Is it because there is a resultant force acting on it because of gravity?
Yes. Yes. There is a net force acting on the ball due to gravity. Because F net is not equal to 0 in this case. F net is equal to force of gravity. Well, in the y direction, yeah, it's negative. Conservation of momentum is only valid if F net is equal to 0. Yeah.
Is that excluding drag when you throwing the ball at a wall or something?
No. Drag would be a net force. However, it can be approximated to be negligible. Then we can say this is true.
Oh.
Yeah. Well, now you're thinking, well, this got much harder because now we don't know when to use conservation of momentum, right? No. In this scenario, there is momentum being conserved. Momentum is actually always conserved as long as you choose the system properly. So then, what is conserved in this scenario? So the answer is choose system wisely. What is exerting the gravitational force onto the ball? Huh?
Gravity?
No, gravity is not exerting gravity. Something is exerting gravity, but what is that something?
Earth.
Earth! if we chose the ball and the earth as our system, we can apply conservation of momentum in this problem and it'd be perfectly fine. So then P final does indeed equal P initial, where the final would be mass of the ball times the final velocity of the ball plus mass of the earth times the final velocity of earth. This is equal to mass of the ball times the initial velocity of the ball plus mass of the earth times the initial velocity of the earth. This is indeed true. And it will give you that relationship of free fall that we would expect. However, the earth is massive. Meaning, you're going to have a very, very small change in the velocity of the earth, so much so that it's unmeasurable. It's not only unmeasurable because the velocity change is going to be so small, but it's so massive. Like, how do you measure the speed of the earth? Well, with a ruler? Clearly that's not going to work. So technically, you can apply conservation of momentum to kinematics problems, or for free fall and things like this, and it should be okay. The only thing is it's not practically feasible. So conservation or momentum is always conserved, but it's not always useful. You have to choose your system wisely. Now we're going to look at a few different types of collisions. We're going to introduce two right now. We're going to introduce one, or another one, after we discuss this topic of energy. The first one is called perfectly inelastic collision. This is the scenario where particles collide and stick. Particles collide and stick. So that Bob scenario running onto a cart is an example of a perfectly inelastic collision, because they start off as two separate entities and then in the final scenario, they are moving in unison. So in this scenario, we would have some particle A and B coming together, and then afterwards, after they make contact, they travel as a single unit. And in this scenario, the momentum values or the momentum expressions will look like this. Mass times A times the velocity of A plus mass of B times the velocity of B. But in this scenario, after they clump up together, they are moving as unison. Oh, sorry, these are all initials. In this scenario, then it's mass of A plus mass of B, and they're both moving at some VF. The second type is an explosion. Essentially, this is the opposite of a collision, or the opposite of the inelastic collision. In the inelastic, you have multiple objects forming one. In an explosion, you have a single object that explodes into many. So this is particle disperses too many. So our system, initial system, you will want to be the entire object. And then later, this part's gonna go that away. This part's gonna go that away. Oh, let's make it easy. Let's say one goes straight